Afternoon all. In continuation with the morning session, we're going to solve a design problem related to masonry structures. I'm going to use the aid of SketchUp, the software SketchUp, so that it's much more easy to understand how the entire principle works. So let's just go through the question. Wall under a uniformly distributed load, which is axially loaded, and it's an unstiffened solid wall. Design an interior cross wall of a two-story building to carry a 100 mm thick RC slab with 3 meter ceiling height. The wall is unstiffened and it supports a 2.65 meter wide slab. Live load on the roof and floor is 1.5 kN per square meter and 2 kN per square meter respectively. Weight of 80 mm thick terrace is 1.96 kN per square meter and weight of floor finish is 0.25 kN per square meter. And the things which we need to assume over here is, number one, the wall thickness, two, the crushing strength of masonry unit, which is brick over here, and three, the type of mortar. So, like I said, as I already designed this, modeled this in this particular software. So, as you can see, this is a two-story scenario where you have your first floor and you have your terrace. Our motive is to design the wall which is in this particular space. This is the masonry wall in which we want to design, and it is this thickness of the masonry wall that determines whether it can carry the load of the above stories or the above live loads. Now let's just quickly go into the general interface of how the entire design procedure works. So the first thing is that you need to calculate the total load that is happening on top of the particular designed wall. For instance, the live load which is on the terrace, number two, the live load which is on the floor finish, the dead load which is happening on the terrace, the dead load which is happening on the floor finish, the first floor, and the self weight of the masonry wall units. So all these combined together will be the total load that is happening on top of the masonry wall itself. Now, as far as the procedure is concerned, the first thing, as soon as you calculate the total load that is happening on the masonry structure, the next thing is that you need to calculate the effective dimensions of a particular structure. For instance, the effective dimensions for this particular structures will be the effective height, the effective length, and the effective thickness. Effective height as in the height which is happening from the bottom support to the top support. Effective thickness is nothing but the thickness of the wall, and this is dependent upon the specifications given by the code. And the effective length or effective span, which is nothing but the lateral dimension of a given wall. Now, since it is mentioned that this is an unstiffened solid wall, we are not worrying about the effective length over here, since there is no stiffening members that are happening over here, which will make it a stiffened wall. Since this is an unstiffened wall and we don't have any lateral support systems which are happening adjacent to the wall, we need not worry about the effective length. The only things which we are concerned over here is the effective height and effective thickness. So this is the code in which we are going to go through. That is IS 1905 1987. Again, it's reaffirmed in 2002. It's used for unreinforced masonry. Diving into it, the first thing you need to go through is a few tables. Now, table 1, which gives the mixed proportions and the strength of mortar for a particular masonry. In this column 2, you have all the different grades of mortar, and in column 8, you have the minimum compressive strength it can offer by the end of the 28th day in Newton per mm square. Moving on from table 1, let's go to table 4. Table 4 gives the effective heights of the wall, and effective height is dependent upon the support conditions. Whatever the support condition is present, according to that, we will have to multiply a factor which will give us the effective height. Next, effective length, which is given in table 5. Now, we are not concerned about the effective length, but nonetheless, based upon the different types of stiffening members or based on different types of lateral support systems, we will have to measure the effective length by multiplying an appropriate factor, 0.8 times L, 0.9 times L, 1 times L, respectively. Next, let's move on to table 8. This is an important table. this this table gives the basic compressive stresses for masonry that need to be considered in order to progress the design further. For instance, the basic compressive strength is given in Newton per mm square. So over here, corresponding to the masonry units, which height to width ratio does not exceed 0.75. That means that it has a limit. Anything that is exceeding 0.75, the ratio 0.75, this particular table will not be applicable for it. And the crushing strength in Newton per mm square is not less than these values. These values which you see in the first row over here, just above these numbers, is nothing but the crushing strength in Newton per mm square. Now, based on the given crushing strength or assumed crushing strength, and based on the assumed mortar type, which is given in column 2, H1, H2, M1, M2, etc., we will have to identify the corresponding basic compressive stresses that it can offer. Now, it is this stress to which we will multiply certain factors like stress reduction factor given in table 9, shape modification factor given in table 10, and another factor called area reduction factor, which is given by the expression K is equal to 0.7 times plus 1.5 times A. Now, let's just proceed with the problem. There's an already pre-solved problem in this regard. So as you can see, we are assuming a wall thickness of 100 mm, a crushing strength of the brick is 10 Newton per mm square, the mortar type is M1. So as you can see, the wall thickness is assumed to be 100 mm. It's an assumption. You can assume more, you can assume less, but as far as this problem is concerned, we have assumed it as 100 mm. Now, the assumption over here ultimately has to satisfy the design criteria. Your assumption should be validated by checking with the total compressive, the total force that is happening on top of it. If it is resisting that particular said load, that means your assumption is valid. For instance, the actual compressive stresses developed is so and so, which is less than the permissible stresses. So it is satisfactory. That's how we need to validate our assumption. So just let's go back to our problem over here. Now, the crushing strength of the brick unit is 10 Newton per mm square. So it is given in the question, it's given in the data. The mortar type is M1. So just going back to our table over here, the mortar type is given as M1. This is table 8. The mortar type is given as M1, and the crushing strength of the brick unit is 10 Newton per mm square, which is over here. The crushing strength of the brick is 10 Newton. So whatever that is correctly coinciding to that particular point, which is 0.96, is taken as the basic compressive stress in Newton per mm square, which has been said here. The combination of these above mentioned brick unit and mortar mix results in the basic compressive stress of 0.96 Newton per mm square. Now, the critical section is subjected to maximum stress is at the ground level. What this means is that for any given structure, not just this, the maximum amount of load is happening on the bottommost part. Ultimately, it is the foundation which takes most amount of load, but then if we are dividing a masonry structure into pieces, even masonry walls will come into picture in resisting the loads. So the maximum amount of load is being borne by the bottommost masonry wall. So we need to design for the critical section of this particular masonry wall. The load at this level is, now this is just a simple load calculations as you have already seen reinforced concrete structures, design of reinforced concrete structures. It's the same process at the ground level. The loads at this level are length into breadth into thickness into the density. So that is 1 into 1 into 0.1 into 25, which is nothing but the density. The weight of 80 mm thick lime terrace, it is 1 into 1 into 1.8, which is nothing but 80 mm meter into 24.5, which is the density of the lime mortar given over there, and of course the live load for a given set terrace. Now we are going to calculate the loads for the terrace and the floor separately, and we're going to add them together. So for terrace, the total amount of load obtained, including live, is 5.96 kilonewton per square meter, and for floor, which is at the bottom level over here, including the live load, it is 4.7 kilonewton per square meter. Assuming the unit weight of brickwork is 20 kilonewton per meter cube, that is the unit weight of the brickwork, we need to calculate the self weight of this given given masonry wall. So the self weight of the wall is again nothing but length into thickness into height and the density. Here, since we are going for two walls over here, both self weight of the walls have to be considered, both weight of the walls have to be considered over here. So we are going to multiply with the number 2. So 1 into 0.10, which is nothing but the thickness, into 3 into 20. 3 is nothing but the height, into 2, which is nothing but 2 number of walls, which completely sums up to 12 kilonewton per meter. That will be the total self weight per meter that is happening by the virtue of walls. Now the total load on the wall length is complete sum of everything, which is 5.96 plus 4.7 into 2.65 plus 12. 12 is nothing but your self weight over here. Now you might wonder what this 2.65 is. 2.65 is nothing but the width of the slab. That means this is your 2.65. As you can see, the length from this point to this point is 2.65. This is the width of the slab. That means your masonry width, the width of the masonry wall is going for 2.65 meter, which is nothing but the room dimension. The dimension of the room in width is 2.65 meter. So we have just multiplied that factor to apply to the entire span of the masonry wall. Now once everything is done, multiplied, you get a total load of 40.25 kilonewton per meter. Now this is all the load calculations. This is typical. This is usual in most of the design calculations that are involved in RCC, steel, or masonry structures. But in masonry, from this point onwards, it's much more codal specific. So the first thing you see over here is effective height. Since it is fully restrained, and we know that it is fully restrained because there are two slabs on either side of the masonry wall, both on top and bottom, they are completely restrained. There is no lateral or rotational displacement that is happening on either side of the wall, both on top and bottom. Even on the lower levels, both on top and bottom, it's completely restrained. So in such case, if you're going back to your code table 4, in table 4, lateral as well as rotational restraint, which is nothing but fully restrained at top and bottom, the effective height will be 0.75 times its clear height, 0.75 times h. So the same thing has been done over here, 0.75 times into 3000 meters. The effective height will be given as 2250 mm or 2.25 meter. Moving on, effective thickness. Now the effective thickness for a solid wall is the effective thickness. The effective thickness of the solid wall is same as an actual thickness, because when we are talking about solid walls, it's usually the same. There is no factor that has to be multiplied to calculate the effective thickness. But if you are going for something like a hollow wall, then there are certain things that you need to calculate, not calculate exactly. You need to consider the thickness of individual leaves that will compose the entire hollow brick or hollow masonry unit. So let's just not worry about hollow bricks now. Effective thickness for a solid wall, it is same as the actual thickness, so it has been taken as 100 mm, 0.1 meter. Moving on, the slenderness ratio. The idea of effective height or effective length is to ultimately get the slenderness ratio of that particular wall. So slenderness ratio is nothing but the effective height by effective thickness. 2250 by 100, which gives you 22.5. This must not exceed 27 for a two-storied wall as per IS 1905. This means that if you come back to your table, in table 9, as you can see, the stress reduction factor for slenderness ratio and eccentricity, the slenderness ratio is maxed out at 27. There is no factors or there is no eccentricity stress reduction factors given beyond 27, the SR ratio of 27. That is the reason why it has been clearly mentioned that this must not exceed 27. If it is exceeding 27, we ought to reiterate the thickness of the wall or the height of a given particular slab. Next, eccentricity, let's just consider it 0 over here. We're not going to take that into picture as this is a completely uniaxially loaded wall, or as our question suggests, for an axially loaded unstiffened solid wall. This is the most simplest form of design that can be. Next, stress factor, which is nothing but Ks. It is directly related to the eccentricity factor, eccentricity aspect. Stress reduction factor, which has to be multiplied to the basic compressive stresses that has been obtained from table 8. If you remember, the 0.96 value from the compressive crushing strength of 10 to a mortar type of 0.96, this particular value 0.96, we will have to multiply this stress reduction factor to that particular value in order to get our permissible compressive strength or allowable compressive stress. Next, the stress reduction factor over here is 22.5 and no eccentricity involved. So let's just go to 22.5, which is somewhere in between 22 and 24. Yes, linear interpolation is allowed. You can do linear interpolation to get a much more accurate value. But since over here we're dealing with eccentricity, and the eccentricity over here is 0, anything divided by 0 is 0. So eccentricity of the loading divided by the thickness of the member, which is nothing but 0.1 mm. 0 by 0.1 mm, 0.1 meter will be 0. So we are concerned about the first column over here. The remaining we can just opt out. So for a stress reduction factor of 22.5, if we are going to multiply the Ks value, it will be 0.55. That is after linear interpolation, we get 0.55. Please note the corrected version. It is 0.55. It's not 0.455. Moving on, once the factor is multiplied to the basic compressive stress, we get a total factor of 0.53. Now, this is the allowable compressive stress that can be existing in a particular masonry wall. Now, the idea is the actual compressive stress is developed as nothing but total load by the area of loading. The total amount of load that is happening on a structure by the area of loading. Area of loading here as in the, let me just move this aside so that it's more clear. The total load that is happening on this particular wall, on this particular area, that is the thickness of the masonry wall, unit thickness is better word for this. So the total amount of load that is happening on the lowermost thickness of the particular masonry structure is what the area of loading is all about. So the actual compressive strength developed is equal to the total load by area of loading, which is nothing but 40.25 into 10 power 3. This is the value which we have got in the very beginning, the total load, divided by unit length into the thickness of the masonry wall. That gives us 0.42 Newton per mm square. Now this is less than the factored load, which is 0.53. So hence we can state that since the actual developed stress sigma c given as sigma c here is less than the permissible stress factor with a choice of 100 mm thick wall is satisfactory. That means the assumption which you have made in using the 100 mm thick wall for that particular masonry structure is satisfying the condition of all the loads that are implied on top of it. Again, however, one may want to provide 1 brick thick wall as a minimum thickness, so provide 1 brick thickness. Yeah, if you want to go for a little adequate safety, yes, you can go for another slightly larger thickness, because the thickness of the brick should be slightly over 1 brick, which will give you a better resistance to other implied loads. So This is an example. This is a walkthrough of an entire design for a axially loaded unstiffened solid wall under UDA. We'll proceed with more problems in further in the similar manner. I've already pre-solved some examples. We'll discuss with those examples as well. You can leave comments, or you can leave emails, or you can just reach me out on the said information below, and we'll proceed further.